Here in section 4.3, we are going to talk about a binomial distribution. Okay, so this is a specific type of discrete probability distribution. And when we say binomial, so bi meaning two, these are probability experiments that have two distinct outcomes. So in order to determine whether a probability experiment is binomial, we say an experiment is said to be a binomial experiment if the following four conditions are met. So the experiment is performed a fixed number of times. Each of these repetitions is called a trial. Okay, so we have a fixed number of trials. The trials are independent of each other, so whatever happens in one is not going to change the outcome of another. Right? So, for instance, rolling a fair die. You know, if we're looking at the probability that I roll a 5 and then a 3, well, the probability that I roll a 5 is not going to affect the probability that I roll a 3 on the next time, because they're completely independent of each other. For each trial, there are two mutually exclusive outcomes, and we call them success or failure. Okay, so you can strip those words of their connotations. When we say success, we just mean, did we get the result, the positive result, or did we get the result that we were not looking for? So that would be success or failure. And then the probability of success is fixed for each trial of the experiment. So the probability isn't going to change from experiment to experiment, like with the die. Right? The probability that I roll a 6 is going to be the same now as it is in the next one, as it will be in the one after that. That probability is not changing. Okay? So, the notation we use for a binomial experiment, we have n independent trials. P is the probability of success. So we use Q, which is 1 minus P, is the probability of failure. Okay, and then X is the binomial random variable that denotes the number of successes. I'm going to do this different color so it stands out. The number of successes in n independent trials. Okay, so we're looking at the number of successes out of n independent trials. So let's look at a few examples, just determine whether or not these are binomial. So which of the following are binomial experiments? A player rolls a pair of fair die 10 times. The number x of sevens rolled is recorded. So let's think about this. Is it performed a fixed number of times? Yes, 10 times. So that's good. Are the trials independent? Yes, right? The probability of rolling the die and getting the dice and getting 7 does not impact the other trials. There are two mutually exclusive outcomes, success or failure. This is where you have to kind of shift your thinking a little bit, because you're thinking, well, there's more than just two numbers that could happen, but we're looking specifically at the number of sevens being rolled. So in this case, success would be considered rolling 7, and failure would be considered not rolling 7. Okay, so in that sense, we do have two mutually exclusive outcomes, and the probability of success is fixed, which is true because the probability on the dice, right, is fixed. So this one is binomial. And again, we have the success of rolling 7 versus failure of rolling something that's not 7. Okay, so that one would be a binomial experiment. Okay, for part B, the 11 largest airlines had an on-time percentage of 84.7% in November 2001, according to Air Travel Consumer Reports. In order to assess reasons for the delays, an official with the FAA randomly selects flights until she finds 10 that were not on time. The number of flights X that need to be selected is recorded. So, if we think about those four conditions, first condition is it needs to be performed a fixed number of times. So, you got to read the question carefully, because your inclination might be to say, well, yes, it's performed 10 times, right? They get 10 planes that were not on time. However, that's not how many times the experiment was performed. Okay, 10 would be the number of successes that she wants. Okay, so in this case, this is not happening a fixed number of times because it says she randomly selects flights until she finds 10 that were not on time. So that means if it's the first 10, then she performed the experiment 10 times. If it takes her 100 tries to find 10 that were not on time, then she's performing it a totally different number of times. So this one, right away from the first condition, is not binomial. Okay, and that's because it's not performed a fixed number of times. And then for part C, in a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. Okay, so we're looking, is this a binomial experiment? So do we have an experiment performed a fixed number of times? Yes, they're selecting 4 students. Are the trials independent of each other? Well, in this case, we have a class of 30 students, and 55% of them are female. So does the outcome of one of these choices, okay, so they're selecting 4 students at random, does the outcome of one of those choices affect the others? Actually, it does, because they're pulling from the same 30 students. So, right, if I'm getting the first student and I pull someone who's female, well, now I only have 29 students left in the class to choose from, which means I have now changed the probability of the second trial in the experiment, which, by definition, I've changed the probability. So these trials are not independent of each other, which means this must not be binomial. Okay, so it's not independent trials. So that's the problem with that one. So now that we've looked at what it means for an experiment to be binomial, let's try looking at some probabilities for binomial experiments. So the probability of obtaining X successes in N independent trials of a binomial experiment is given by this formula. So we get the value of the combination, right? N choose X. Okay, so out of the N trials, I'm choosing to have X successes because I'm looking at the probability, right, that X occurs, times P to the X, where P is the probability of success, and then times 1 minus P to the N minus X. Okay, so that would be the probability of failure, right, raised to the N minus X. Okay, and that's because the probability of success, this is where we succeed X times. Probability of failure, this is where we fail N minus X times. Okay, so just however many we don't succeed in. So according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. Suppose there is a random sample of 20 car-owning households. What is the probability that exactly 5 of them have 3 or more cars? Okay. So we would consider success as a household having 3 or more cars. Okay, so we're looking for the probability that we get exactly 5 houses that have 3 or more cars. So this is going to be a combination out of our 20 trials, our 20 households, 5 of them are a success, right? 5 of them have this criteria met. Okay, then times probability of success, well, there's a 35% chance of this happening. So 0.35 to the X, so to the 5th, times 1 minus 0.35, so this is probability of failure, to the 20 minus 5, right? Or to the 15, right? Because if I succeed 5 times out of the 20, then I'm going to fail 15 times out of the 20. Okay. So this gives us, right, so 20 choose 5. So we can compute that. You could use the factorials and all that, or just use technology. Times 0.35 to the 5th, times 0.65 to the 15th, which if we plug and chug these numbers is going to be approximately 0.1272. So what is the probability that in our sample of 20 households that exactly 5 of them have 3 or more cars? That would be about 0.1272. So that's telling us there's about a 12 to 13% chance that that would occur. Okay. Now, when it comes to computing binomial probabilities using the technology, we can use Desmos for this, so I'm going to switch over to that. Okay, and this one is going to be under functions, or you can just type it, but you're going to go to the distribution button, and you're going to go to the binomial distribution button. And notice Desmos helps us out. It tells us it needs to know the number of trials and the success probability. So we saw in the example we're performing 20 trials, and the success probability was 0.35. And there we have our possible outcomes in our binomial distribution. So to make this a little more visible, I'm going to just kind of fix my axes here a little bit. So x-axis is good. Y-axis, we're going to go negative 0.5 up to, actually I'll do even less than that. Just try to zoom in quite a bit more. Negative 0.2, something like that. So this is what our binomial distribution looks like. So we can see here the probability, right, of each of these events occurring individually. Okay, but we can also look at the cumulative probability. So this is more what the graph is going to look like. But notice in the previous example, we were asking what is the probability that we would have exactly 5? Well, we get about 0.1272 is that corresponding value. Okay, so, and then the reason that these are all vertical lines is because this is discrete. These are countable. Okay, so we don't form them into a smooth curve. These are all distinct from each other. Okay. So in the next example, it asks, what is the probability that less than 4 have 3 or more cars? So probability that x is less than 4. Okay, so in order to find this, if we were going to do it manually, you'd have to get, well, less than 4. So that's the probability that it's 0 households, probability that there's 1 household, plus the probability that there's 2, plus the probability that there's 3. Right? These are all the possible outcomes. Less than 4. Now we can look at this on Desmos. Of course we could do it by hand, but then we'd have to use that formula 4 times in a row, and that would just be kind of tedious. So we're trying to get the value for less than 4. Okay, so that's going to be just up to 3. So notice if I put in the value, the minimum of 0, maximum of 3, we go up to 3, right? Everything less than 4. And we get 0.04437, so 0.0444 approximately. So let me just put that there. 0.0444 is our probability that less than 4 households have 3 or more cars in this particular experiment, right, with 20 households in our sample. All right. So then, using the same example, what is the probability that at least 4 households have 3 or more cars? So probability that x is at least 4. Well, luckily for us, these events are complementary because, right, we already found the probability of them having less than 4. So this would just be 1 minus probability that the number of households is less than 4. Right? Because if that's 4, then we've already found all the values less than 4. Now we're going to find all the values greater than 4. So we get 1 minus, we just found that one, 0.0444, which is 0.9336. So the probability that at least 4 of these 20 households have 3 or more cars is approximately 0.9336. And we can check that here on Desmos as well. So instead, I just set the minimum at 4. Okay, and then going up to 20. Okay, and then we get our value. Oh, did I write those numbers wrong? I think I wrote those numbers wrong. Because obviously Desmos knows what it's talking about. We get 0.9556, not 9336. Yeah, so let me just fix those. Sorry about that. Should be 9556. That's better. Okay, yeah, so again, we can do this by hand using the formula, or we can apply the technology. So when it comes to computing mean and standard deviation of a binomial random variable, binomial is much more friendly to us than some of these other probability distributions. So as you can see, we have pretty nice, concise formulas for them that are just involving the number of trials and the probability of success. So to find the mean value, you just take number of trials times probability of success. Standard deviation, you take square root of n times p times 1 minus p. And that's all there is to it. So in this example, with our 35% car-owning households have 3 or more cars, suppose now they did a random sample of 400 car-owning households. Let's look at the mean and the standard deviation. So the mean is 400 trials times the probability of success of 0.35. We get 140. So again, the mean and expected value. So we would expect out of these 400 car-owning households that 140 of them would have 3 or more cars. Okay, and then standard deviation, square root, 400 times 0.35 times 1 minus 0.35, so that's 0.65. So we get 9.54. Okay, so we expect 140 households to have this many cars with a standard deviation of 9.54. So give or take 9.54 households in this sample. Okay. And then here we're looking at graphs of binomial probability distributions. So we've kind of already looked at this, but they just want to emphasize kind of the behavioral changes depending on your sample size, your number of trials, and your probability of success. So let's look down first. So starting with A, if we have 8 trials and a probability of success of 0.2, so notice we're all kind of hugging the lower end down here. Okay, but as soon as we go 8 trials and a 0.5, now we have a little more of that standard kind of bell-shaped curve here, right? It's more symmetric, it's more centered. And then if we go 8 trials with a probability of success of 0.9, now we're moving over all our data to the right. All right, because there's a greater likelihood that it will occur more times, so the higher values kind of get more weight to them. What happens if we drop the number of trials, but still maintain the probability of success? Compare this one to this one. Notice this steeper drop-off, right? So we can see much less likely to occur, at least using fewer trials, right? So the general rule is the more trials, the better. Okay? And then we see when we have 8 trials and 0.2, which actually that's the same as A, right? So we're just comparing again. But then, what happens if we do 70 trials at 0.2? Notice this smoothed out much more nicely into that bell curve shape. This is going to be important later on. Just again, this concept that you want to have as many trials as you can because it's going to make your data more accurate. So, and that's kind of what this describes down here. So, for a fixed probability of success P, the number of trials N in a binomial experiment increase. As this happens, the probability distribution becomes bell-shaped. As a general rule of thumb, we would like N times P times 1 minus P to be greater than or equal to 10, and that would tell us that this distribution will be approximately bell-shaped. And that's good for us for reasons we haven't talked about yet, but bell-shaped curves are ones that we're going to be able to work with very well in statistics, and we're going to work with bell-shaped curves for most of the rest of the semester. So this is just kind of leading us into that. But this is just, again, a brief look at the types of graphs of these binomial probability distributions. So that brings us to the end of chapter 4. So a little bit of a shorter chapter this